Let's now talk about a very important concept when we're dealing with structures that are periodic in multiple dimensions, and that concept is the reciprocal lattice. So let's talk about such periodic functions where, for example, f of r plus capital R is equal to f of r for all lattice factors r that we have in the periodicity structure. So just to basically set the scene, let's say we're dealing with a two-dimensional structure like this, then you basically see that every time you translate over a certain lattice factor r like this, then the structure doesn't change. And basically, if you take integer linear combinations of any of these points here, any of these lattice factors, you end up again with a member of that same family. So this is why this family of vectors is called a lattice. So we already introduced them in the context of Bloch's theorem, but this is a quick reminder of what we're dealing with this lattice over here. Okay, so these are functions we're looking at, periodic on a lattice. What we're now going to do is pause the video and write down the Fourier transform of such a function and see if you can interpret what that actually means from a physical point of view. Okay, for any sufficiently well-behaved function f of r, we can write down its Fourier transform, continuous Fourier transform. It's a three-dimensional integral in the most general case of 3 dimensions of a certain function g of k, which is the Fourier transform, times exponential minus j k r, and then we integrate out over dk. So this is the definition of the continuous Fourier transform, but can we actually interpret this from a physical point of view? Well, we can obviously, because this guy over here, this complex exponential, as you know, this is a plane wave, right? So what we're basically saying is that any function f of r can be written as a, well, let's not call it a sum because it's an integral here, so let's say a continuous collection of different plane waves with certain k vectors over which we sum or integrate, and each of these plane waves has a certain amplitude, and that amplitude is given by this Fourier transform here, j of k. Okay, so that's something we can write down for any function, but we haven't really exploited the fact that our function here is periodic. So that's our next step. Pause the video and see what the consequences of periodicity are. So if our function is periodic, that means that we have to obey that condition over here. So for any lattice factor capital R that we have, we should have that f of r, which we've written down here. That should be the same as f of r plus capital R. And then just we plug this change into the definition of our Fourier transform. So like this. And the thing that changes here is actually this exponential. So k capital R exponential minus j k little r dk. So these things should be the same. So if we look at what's happening inside the integral here, then we can focus, for example, on this part and on that part, and asking that our two expressions here are the same basically boils down to the fact that asking that the stuff we have here in red, that is the same. So we should have, if you write it down, that g of k should be equal to itself times this complex exponential minus jk of r. And again, I've written this down here for a specific lattice factor r, but our function is periodic on all possible lattice factors r that you can think of. So it's important to keep that in mind over here. Okay, so now we can ask ourselves the question, when is this particular expression true? Well, there's two ways of achieving this. The first thing is the rather trivial case where we have that the Fourier transform is equal to 0. Then that expression will hold. And the second case is when we have that this complex exponential will actually evaluate to unity. So exponential minus jkr, that this thing should be equal to 0, again, for all lattice factors r. But this is a very important conclusion because this means that our Fourier transform g of k will actually be 0 most of the time, except for very specific situations, very specific discrete cases where this particular condition holds, exponential minus jkr equal to 1 for all possible lattice vectors. So rather than having a continuous Fourier transform, we have actually a set of spikes. Rather than having a continuous integral, we just have a discrete sum. So this means that our periodic function can be written down as a sum of plane waves with certain amplitudes, but the k-vectors of these plane waves that we use have to satisfy this particular condition. Okay. So that's an interesting conclusion, an interesting step forward. But the next question we have to answer is, can we actually calculate what these k-vectors are that we need? So let's call the family of these k-vectors that we need in our sum the family of g vectors here. And these we will call the reciprocal lattice vectors. So reciprocal lattice vectors. Why do we call them like this? Well, there's an exercise that you can do where we show that this family of k-vectors is actually again a lattice, meaning if you take integer linear combinations of them, you again end up with this member of the same family. And why are they called reciprocal? Well, if you just look at the units over here, so our lattice vector r, which is a vector over which you translate the original lattice in the spatial coordinates to get the same lattice, that of course has dimensions meters. And in order for this thing to be dimensionless, this means that the k-vectors here have to have dimension 1 over meter, the reciprocal of meter, and hence we call these guys, this family J here, G rather, the reciprocal lattice, consisting of reciprocal lattice vectors. Right, so the task that we have now is, given our family of ordinary lattice vectors, which indicate the symmetries, the translation symmetries in the system, can we come up with some sort of recipe to find the k-vectors that we need to build our sum of plane waves here? And we need to build them in such a way that this exponential over here is 0, or to write it in a different way, that we have the scalar product of these guys should be equal to an integer multiple of 2 pi. And again, for all possible lattice vectors that we have. So that's the task we have. It seems a bit complicated because we're dealing with an infinite family of vectors and an infinite family of reciprocal lattice vectors. So let's see if we can get a handle on this by trying to simplify things by making use of the primitive lattice vectors and the primitive reciprocal lattice vectors. So just as a quick exercise, pause the video and see if you can write down for a simple cubic lattice with period A, if you can write down a general expression of any lattice vector R as a function of the primitive lattice vectors. So a very quick exercise to recap the concept of primitive lattice vectors. So for this cubic lattice with periods A in all 3 dimensions, you can write down any lattice vector R as L times A unit vector in the x direction plus m times A unit vector in the y direction plus n times A unit vector in the z direction, where L, m, and n are integers. And you can basically say that this here is our first primitive lattice vector, A1. Here we have A2, and A times 1z is A3. For the case of this cubic lattice, they all have the same magnitude and 3 orthogonal directions, but of course your mileage may vary depending on the type of 3D structure, periodic structure that you're studying. The important thing is that we can write our lattice vector as linear combinations of these guys, these very small, the smallest, the primitive lattice vectors. And we can obviously play the same game for the family of reciprocal lattice vectors, where we can have, for example, an L prime, and then we identify a B1, smallest in a certain direction, and then we have n prime B2 plus n prime B3. So rather than having an infinite family of vectors here, we seem to be able to focus just on the primitive lattice vectors and the primitive reciprocal lattice vectors. So now pause the video and write down this condition here as a function of this expansion here in this basis set, and think about possible ways of trying to satisfy these conditions. Okay, so if you just copy and paste the fact that the scalar product G with R should be equal to an integer multiple of 2 pi, yeah, then we just trivially have L prime B1 plus M prime B2 plus N prime B3 scalar product with L A1 M A2 and N A3. Okay. And for any possible combinations of L's and M's and N's and primes and stuff like that, there should be a certain integer capital N such that this is just an integer multiple of 2 pi. So that's the goal we have. So let's see if we can figure out a way of satisfying this. And if we stare at this for a while, perhaps we might think, well, one way of satisfying this condition is that if we expand this thing over here, we will all have these products basically of a certain A, let's call this AY, and a certain B. And if we make sure that all of these guys are integer multiples of 2 pi, then we're in business. And one particular case of doing this, which is a little bit more restrictive, is the following, is saying that this scalar product is actually 0 if I and j are different, and is actually equal to 2 pi if they are the same. So shorthand here is writing this as follows with this Kronecker delta thing here. So if this is the case, if we somehow find a way to satisfy this condition, then this condition up here will be automatically satisfied because we end up with all sorts of integer multiples of 2 pi. Okay. We're almost there because we've kept on simplifying and simplifying stuff until finally we end up here. So now, given 3 A vectors, can we find 3 B vectors that satisfy this condition? So that's not so straightforward, but if you think about this for a very long time, you might be able to come up with something that's based on the observation that if you have 2 vectors, let's call them x and y, and you take the cross product of these 2 vectors, then you end up with something that by definition, by construction, is orthogonal to both x and y. So because it's orthogonal to x, this means that if you take this scalar product, this thing will be equal to 0. And using this as some sort of inspiration, you might think of constructing your B vectors as follows. So you might say that, let's see what happens if we define B1 as 2 pi times the cross product A2, A3, divided by the triple product A1, A2, A3. Okay. And then we define something similar for the B2s and the B3s. So for B2, we have A3 times A1. And then we have the same denominator, A1, A2, A3. And then it will come as no surprise that for B3, we have 2 pi A1, A2 divided by the same denominator again. Okay, A2, A3. Right. So perhaps this falls a bit out of the sky here, but what you can easily do for yourself is pause the video and try to convince yourself that if you have expressions like these and you plug them into that condition over there, if you take the scalar product, A1s with B1s, A1 with B2, and so on and so forth, that you really end up with something that satisfies this particular condition. So that's a very nice exercise. Pause the video and convince yourself that these B guys are really the ones that we're after. Okay, let's verify what's going on. So we need to take the product of, let's start with taking the product of A1 and B2. Let's do it differently. Let's do A1. Well, it doesn't really matter. The important thing here is that B1, if we take the scalar product with either A2 or A3, we will have 0 as we need for this expression, simply because of this condition over here, that A cross product with A3 will be orthogonal to both A2 and A3. So that part of the equation is taken care of. B1 is orthogonal both to A2 and to A3. The question is, if you take the scalar product A1 with B1, do you end up with 2 pi? Well, if you multiply here on the left-hand side with A1, right, then you really see that numerator and denominator here become identical. This thing becomes 1, and you really end up indeed with 2 pi as is required. So that's good news. The same story we can play for B2 and B3. Again, B2 is orthogonal to A3 and A1. And if you take the scalar product with A2, then, so if you have A2 here on the left-hand side, then we have A2 over there. So it's a little bit more involved here in the sense that we just don't immediately can say that numerator and denominator are the same. But if you think back to the properties of these triple products, then you know that if you sort of like cyclically rotate the 3 different elements around, then indeed you end up with the same thing. So here we have a cyclical permutation of A1, and then we go back to the beginning, and then indeed we have A2 and A3. So also this thing becomes 1, and then you can verify for the final thing, B3, that it satisfies the same condition. So we have indeed what we're after, and that's the following. So that was a rather long calculation, but let's again wrap up what we've learned so far. We've learned in the end that if we have a function that's periodic on a certain lattice with lattice vectors capital R, that we can write this as a discrete sum of plane waves with a certain amplitude. And the plane waves that we need are plane waves with certain k vectors. And these k vectors we can find by looking at members of the lattice that's formed by these guys over here, these b vectors, which are the primitive reciprocal lattice vectors. So this is a very important concept that we will be able to make use of in the next chapter of our stories.